Now we will start with another small topic, temperature dependence on resistance as well as resistivity. So as we know from our resistance law that resistance is rho into L by A, where L is the length of the wire, A is the cross-sectional area of the wire, and rho is the resistivity. And from our drift velocity expression we have found m by n e square tau L by A. So here we know that resistivity, if you look at the expression for resistivity, which is m by n e square tau, from here, as electrons charge and mass is constant, you see that resistivity generally depends on the number of electron as well as the relaxation time tau. So generally what happens in general metal or general conductors, the relaxation time would decrease as the temperature increase. So what we see, as you give temperature, the relaxation time decreases, tau starts to decrease, so therefore rho starts to increase. So the graph generally that we get for conductors, that would be sometimes for certain materials the graph would be something like that. For certain materials the graph are like this, which is a increasing graph if you plot versus resistivity with temperature, which is an increasing graph with the temperature. Now if you take a semiconductor, for semiconductor what happens is, though the temperature with the temperature increase, the relaxation time starts to decrease, but at the same time the number n starts to increase very heavily, and both the effect, though the relaxation time decreases, the number of electron per unit volume, this n number is very huge in the case of semiconductor, and therefore what we see, there is as the temperature increase, n starts to increase, and therefore resistivity starts to decrease, and the curve generally is like this. So as the temperature increases, the resistivity for a semiconductor start to decrease, whereas the resistivity of a metal or a conductor would start to increase with the temperature. And if we see the relation, which suppose we want to calculate resistivity at a certain temperature T, which is equal to rho naught into 1 plus alpha T minus T naught. So this is the expression for the resistivity at the temperature T, where the resistivity at T naught would give me as rho naught. At the temperature T naught, my resistivity of that material is rho naught. Alpha is the temperature coefficient. Alpha is called the temperature coefficient, and this is the expression that is given for the relation between the resistivity with the temperature. So suppose a temperature T minus T naught, from T naught at a temperature T naught I had the resistivity of the material as rho naught, and I increase temperature to T, and therefore we get my resistivity rho T. The increase of this temperature, suppose if it is del T, then my expression would become rho T is rho naught into 1 plus alpha into del T, which is the increase of the temperature. So this expression gives me the relation of resistivity with the temperature T. The same way we can also, there is a similar expression which is given to explain the dependency of the resistance with the temperature. Suppose at the T temperature I want to find the resistance of a certain material, which is given by R naught into 1 plus alpha T minus T naught. This is same as it is given. RT is a temperature at T. RT at T temperature resistance, which I want to find. Then I need to find a reference temperature R0, and I need to know what would be the resistance R0 at the temperature T0, and I also need to know the temperature coefficient of that particular material, and then I would be able to calculate for a temperature increase what would be my resistance at particular temperature. So let's talk about resistors. As we already learned from Ohm's law, and we also know resistors are the type of electronic devices that provides the necessary resistance to the circuit. Now generally resistors are of two types. One is the wire type of resistor. So you take a wire, generally manganese, nichrome, and all these wires, they are wounded together, and that's how they are created. The resistance is created, and that's how they are used as a resistor. And the second type of resistors are carbon resistors. These are the wire resistors. This is the carbon resistors, which are generally used in all the electronic circuits. And there is a way of studying the color code of this resistors. So they are very small cylinder shape, and since the carbon is abundantly found material, so it is made up of carbon and very easily available and very cheap also. So they are cylindrical in shape, and two sides are there, and they are black in color. But generally this resistors have 4 lines on them, and these lines are of some specific color, and we need to know to read this color to find out the resistance of this particular resistor. So we will learn what is the color code. The color code, if you want to remember the color code, it's very short way to remember as BB Roy, GBV, GW. So this is the way to remember the color codes. BB is black and brown, ROY, Roy is red, orange, yellow, GBV is green, blue, violet, and GW is grey and white. So this gives the numbers from 0 to 9, and then I have a multipliers, the column where they have the black has multiplication of multiplier of 10 to power 0 or 10. Brown has multiplier of 10 to power of 0, which is 1, 10 power of 1, which is 10, 10 power of 2, which is 100, and so on. While white has 10 power of 9, whereas gold and silver has 10 power of -1 and -2. Negative side is the multiplier. Now this generally, these 3 bands, out of these 3 bands, the first 2 bands gives a significant number of the resistance. The third band represents the multiplier, and the fourth band gives the tolerance of the resistance. So suppose I have the first 2 bands as R, that is red, and G, that is green. Suppose red, green, and orange are my first 3 bands, and the last band is silver. So this 4 bands, suppose I have in my resistor. How to calculate the resistance of this particular resistor? As I told you, the first 2 bands give me the significant number. First is R, so my first significant number is 2. Next is green, so my significant next number is 5. So my 2 significant number is 25. Next, third band gives me the multiplier. It means I have to multiply with whatever the multiplier that represented by the third band. Third band is orange, and orange has a multiplier of 10 power 3. So 25 into 10 power 3 ohm is my resistance of this particular resistor. Now the last band is silver, which gives me plus minus. Silver has a tolerance of 10%, so which give me the tolerance of plus minus 10% with the color. So sometimes this the fourth line is absent. If there is an absence of fourth line, there is no color code, then we have to take the tolerance as 20%. If it is silver, then the tolerance is 10%. If it is gold, the tolerance is 5%. And the first three codes give me successively, the first two codes give me the first two significant number. So you just need to add them. The first one is 2 and the next one is 5. So you just keep the first two significant number, which is 25, and then it gives me the multiplication. Third band gives me the multiplier of it, and I have orange, a multiplier of 10 power 3. And then the last I have a line. If there was no line, I would have taken 20% as my significant number. Since I have silver, so silver has a significant tolerance, a significant tolerance. Tolerance would be 10% for silver. So my resistance here is 25 into 10 power 3 ohm plus minus 10%. So this is my color code of the color code read or the resistance from the color code of the resistor. This is what is very important for us to know. And now when we are talking about the resistance and the resistivity of the material, generally when we see the resistivity increases from non-conductor to a semiconductor to a conductor. So in this way the resistivity generally starts to increase, or in opposite way the resistance of the resistivity start to decrease. So a material which is a non-conductor, the resistance would be very high, and for a semiconductor resistance will be lesser. For a conductor the resistance will be very low, and same way the resistivity of the material also would include this way.